Hi, this is Sonia Doucette. In this video, I'll show you how to calculate half-life when you know the rate constant for a nuclide, and also explain, or at least give one example of why half-life is important and why it can be useful to know. This problem says that the rate constant for sodium-24 is 4.63 times 10 to the negative 2 per hour. What is the half-life of sodium-24? So the equation for half-life is T 1/2, which represents the half-life, and it's 0.693 divided by K, which is the rate constant. And you're given the rate constant for sodium-24 in this problem. So all you have to do to find the half-life is divide 0.693 by 4.63 times 10 to the minus 2 per hour. So per hour basically means 1 over hour. And when you do the math there, you'll get, rounded to the correct number of sig figs, 15.0 hours. So that's your half-life. So what can you do with that? Well, the half-life is defined as the amount of time for a quantity of something, in this case the isotope, to fall to 1/2 of its value. So if we think about what's happening over time to the sodium-24 isotope, because it's radioactive, and that means it's decaying, and when it does decay to some other element, it disappears. So let's look at a graph of what's going on here. And let's just say on the y-axis you have 100% of the original sodium-24 present, and at the bottom of the y-axis you have 0% present. And then we'll look at half-life. We'll put half-life on the x-axis. So you have 1 half-life, 2 half-lives, 3, you can keep going. I'll go up to 7 for the purpose of this example. So at 0 half-lives you have 100% of your sample. So I'm going to put a dot at 100 on the y-axis and 0 on the x-axis. And then 1 half-life would be the amount of time for that 100% to fall to half of its value. So a half of 100% is going to be 50%. So at 1 half-life, you're going to have 50% of your original sample remaining. At 2 half-lives, you'll have half of that 50%. So you'll have 25% of the original sample remaining. At 3 half-lives, half of 25 is 12.5, and then 4 half-lives, half of 12.5 is 6.25. So at 4 half-lives, that's how much will remain. At 5 half-lives, you're getting really small. So the x-axis there, because I'm running, or sorry, the y-axis there, because I'm running out of room, is actually 3.125. So that's half of 6.25. And then at 6 half-lives, you only have 1.5625 left. And at 7, you only have 0.78125% of your original sample remaining. So as far as the sodium-24 isotope, this isotope is used medically in the studies of human blood. So knowing the half-life can help you figure out how long you could run a study, just for an example. So let's say you look at 6 half-lives. Just pick one randomly. So 6 half-lives times each half-life being 15 hours, that means 6 half-lives is about 90 hours, which is 3.75 days. So somewhere between 3 to 4 days. So at that point, you only have 1.5625% of your original sample remaining. So as the percent remaining gets smaller and smaller, the amount of radioisotope present is often less than the detection limit of an instrument, for example, that you're using to measure that quantity. So the point is, there is a finite limit to how long you can use particular isotopes to determine particular things in studies such as this one. So you could conclude that that sodium-24 isotope, if you were tracing some process in the blood by using that isotope, you couldn't trace that process for more than about 4 days. because at that point there's hardly any sodium-24 remaining. And that is one huge application of these isotopes. They're also used for dating, carbon-14 dating, lead-210 dating. There are all sorts of applications, but knowing the half-life is critical in all of these applications.